Okay, guys, this is problem 4 for homework 4. Radial and transverse components given R and theta as functions of time. So let's first read the problem statement. During a purse sailing ride, the boat is traveling at a constant speed of 37 kilometers per hour with a 200-meter long tow line. At the instant show, the angle between the line and the water is 30 degrees, and it's increasing at a constant rate of 2 degrees per second. Determine the velocity and acceleration of the purse sailor at this instant. So we will first start with the knowns and unknowns and label. So we know that this R does not change. It means constant, 200 meters. The angles was changing, so we come up a relationship between this point, this ER, or as Professor Chi mentioned in lecture, UR. Let's keep it consistent with the notation. R theta, point P, this R, this is theta. So first, let's write down the givens. So velocity of the boat, given, which is 37 kilometers per hour, approximately 10.278 meters per second on the I-hat direction. So this, label this y, x. We know it's at a constant. So we know the acceleration will equal 0 of the boat. We know that R is 200 meters, which is constant. That means R dot equals 0. R double dot equals 0. We know the initial angle theta equals 30 degrees. We know theta dot, the rate that is changing is 2 degrees per second. We change it to radians, we get 0.0349 radians per second. Theta double dot equals 0. Then we type R relative motion relation, so we know velocity of the purse sailor plus velocity of the boat plus velocity of purse sailor with respect to the boat. And we know the acceleration as well. With respect to the boat. Now using radial and transfer components, you get this one equals R dot times U R plus R is about theta. Take the derivative. AP R dot dot minus R dot. It should be R. Theta dot square. R plus R theta double dot plus 2 R dot theta dot theta. So let's plug in the values. So all these values, this one, this one, and this one. So we're plugging all the values from here. We know r dot is 0, so this is going to be 0. R is 200 times theta dot, 200 times this. So we'll get 6.8981 per second. For the acceleration, we'll get minus 0.437 UR meters per second square. Now we want to change this is in radial and transfer components. We want to change it to rectangular coordinates. So if we go here, we will do velocity P with respect to B equals 6.8 times sine 30 degrees. That gives us the x component 6.981 cosine 30 degrees. Y component 1 meters per second will equal 3.491 plus 6.046 meters per second. And then we do the same thing for acceleration. So we get minus 0.2437 cosine 30 minus 0.23137 sine 30 projection meters. So if we substitute these values back, let's say this is 3 and 4. So substitute 4 and 3 back to 2 and 1. We get equal 10.278 I hat plus 3.491 J hat plus 6.046 J hat meters per second. And this will equals 13.768 on the I hat plus 6.046 on the J hat. for the acceleration, 0 plus 0.211 I have and 0.1219 we have meters per second square. If we want to get the velocity of the first cylinder as well as the angle, we have the I and j components. We take the magnitude of these. So BP equals BPX squared plus BPY squared. So these two values, 13.7 square and 6.046 square. So we plug those in. 13 square, let's just round. 6 square, roughly about 15.04 meters per second. To get the angle, we do tan theta equals y over run. So y over x. So if we want to get the theta, inverse tan, so we get theta equals arc of y over x. Y component, x component, 23.70 degrees. These are for the velocity, angle, and acceleration. Similar, for the sake of time. Acceleration, plug in the numbers similar. Do the magnitude same as over here. So we get 0.244 meters per second square. And the angle theta equals arctan y component x component equals 30 degrees. That is it for this problem.